In the biostratigraphic studies, it is important to know a few conflicting situations and how we tackle them logically. Consider there are two groups of coexisting species or taxa, A and D, found somewhere in the world, and B and C found somewhere in the world. Now, in an isolated succession, I am observing C is above and A is at the bottom. This means C is young, A is old, and in another succession, so this is P1, this is P2. In P2, we are finding B is at the bottom, D is at the top. So, this is a conflict. There can be several ways of explaining it. For example, I can think that, and we have to see as a geologist which one can be correct. Probably here D was there and here B was there, here A was there and here C was there. Now, for some reason D fossil got destroyed, B fossil got destroyed, A got destroyed and C got destroyed. This can be one possibility, but even if you think that, then AD at the bottom, BC at the top, and here AD at the top and BC at the bottom. Now, the geologist has to look at various possibilities. One possibility is that we are dealing here with an overturned succession. A folding can lead to such an overturning. Can you think of any other possibility? Okay, if we think in this way, that with new studies we find AD and BC actually belong to a single group, all are coexisting. In fact, AD and here was BC, BC was destroyed, CB and here was AD and AD got destroyed, here BC was there that got destroyed and here AD was there that got destroyed. Can you think of any third possibility? I take another conflicting situation. There are 4 taxa 1, 2, 3 and 4 and their vertical succession is shown by straight lines. Suppose you have done a sampling from here and you have got 2 and 3 and another person from another place in the world have got 1 and 4 occurring together. Now, here actually in P1 what is happening? 1 and 4 do not co-occur. So, what can be the explanation? You can pause the video, think and then look at one of the explanations. I hope you pause the video. Now, I am giving just one possibility. Suppose 1 was here and then 1 was actually continuing here also, and here for some reason no fossil was preserved. So, in that case you can find a superposition between 1 and 4. The idea is in the field see as much as possible. If this is your study area, you need not just confine here, but you should also see little bit outside your study area. This is, let us say, the planned study area. In that case, not only you cover your study area, but also see outside study area. This becomes an important philosophy in the field work. Also see outside study area can give interesting clues. So, if in the field there are several road sections available, it is recommended to work in all those road sections. Something new might be available waiting for us. Rivers cut natural vertical sections and usually along that roads are also constructed. Now, it can be found that several roads are there at several elevations. All these sections are to be traversed. We will now see more about the graph theory. These concepts are useful if you go into the detail of the biostratigraphic studies. Let us see chain. What is a chain? It is a kind of a non-oriented graph. That means we are going to see a graph where there are no arrows. If A and B are connected, you can move from A to B, also you can move from B to A. Chain is an alternate sequence of distinct vertices and edges. So, here distinct vertex and a distinct edge, one vertex and one edge. If you move, then from here one vertex, another edge, from this vertex another edge, and from this vertex P another edge, and then it stops. It begins and ends in a vertex. let us say in this movement I have given this blue arrow, this is the start and this is the end. Now, we use another term length of chain. What is that? The number of vertices in a chain. What is a circuit? It is a closed chain. So, if I start from here and move, I will finally come back to the same vertex. That is the meaning of the word closed. Now, a circuit of length n, that means of vertices n, is represented by Zn. Since it has got 4 vertices, we call it Z4, the conventional symbol. Chord, an edge connecting two non-sequential vertices. For example, here what are the non-sequential vertices? If I take 1, this 2 has to be skipped and 3 is the other one. So, 1 and 3 are the non-sequential vertices, and if I join them, this line 1 3 becomes a chord. Similarly, you can join 2 and 4, you can join 2 and P, you can join 3 and 4. So, you can then find the chords, and you can think, suppose you are moving from 1 to 2, this is the shortest path to reach, and if you want to take a longer path, then move from 1 to 3 and then from 3 to 2. Although I have used arrows here, remember we have discussed the non-oriented graph, and in the definition of chain we are bringing the arrow. Let us see what is a path. Start from a vertex. For this graph, I start from a vertex 5, then do not touch the same vertex, do not move along the same edge and keep moving. So, from 5 I can go to 6, from 6 I can go to 4, from 4 I can go to 3, from 3 to 2 and then 2 to 1. So, this is a path. Or alternately, from 5 I go to 6, from 6 I go to 4, then from 4 I go to 1. So, that is also another path. Or you can have the prolonged journey 5, 6, 4, 1 you have done, move one step from 1 to 2, that is another path. So, it is obvious that the same graph can have many paths, it is possible. Now, what is a cycle? When a path is closed, starting and ending vertex are the same. For example, in this one, suppose I start from 5 and then I go to 6 and then to 4 and then again from 4 to 5, 5, 6, 4, 5. Starting vertex and the ending vertex are the same. So, we call this as a cycle. Now, consider this 5 to 6 to 4, 5 to 6, 6 to 4, then 4 to 3, then 3 to 2, this much is covered, then 2 to 1 and then again 1 to 4 and then again 4 to 5. So, we started with 5, we ended at 5, but this is not a cycle. So, I put cross mark. Why? Because you can see vertex 4 has been repeated. Since a vertex is repeated, by definition it cannot be called as a cycle. Now, let us see a walk. We have taken the same graph as the previous example. Here vertex and edge can be repeated. Start with 4, I go to 1, 1 to 2, 2 to 3, 3 to 4. So, 4 is repeated, then 4 to 5, then 5 to 6, 6 to 4 again. So, 4 gets repeated and then again 4 to 3. So, we have repeated 3, we have repeated 4, and this repetition is acceptable in the definition of a walk. Now, we will see trail. Vertex can be repeated, but not the edges. Let us see in the same graph 1 to 4, then 4 to 6, 6 to 5, 5 to 4, 4 is repeated and then 4 to 3. In this no edges were repeated. So, we can call it a trail. What is a circuit? A trail and it is closed. For example, here 1 to 4, 4 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 2 and then again to 1. So, we started at 1 and we have come to 1 again, that is the end. So, it is a closed one. Is there any vertex repeated? Yes, 4 is repeated. So, it is a circuit and it is a kind of trail. That means, in this circuit vertex can be repeated, edges cannot be repeated. This definition holds true here also. Okay. Now, we see the definition of a tree. a connected graph without any cycle. Here is a graph and you cannot establish a cycle. That means you starting from a vertex, you are moving through edges going to another vertex, and then finally you will come back in the same vertex without repeating the edge is not possible. Therefore, this is known as a tree, and a collection of trees will constitute a forest, as if indeed in real world several trees can make a forest. Ti and Tb are the two trees, and they taken together, Ti and Tb, will constitute a forest. We will see the definition of a strongly connected graph. An oriented graph, or a kind of path basically, where every vertex can be reached from every other vertex. Once we said oriented graph, we essentially mean a directed graph or digraph. And read the definition again. We are starting from vertex 3. From vertex 3, I can reach vertex 0, I can reach vertex 1, I can reach vertex 2 following the arrows. From 2 I can reach again to 3, and from 2 I can also reach 4. Similarly, if you start from 2, you can reach 3, 0, 1 and also 4. Similarly, if I start from 1, I can reach all the vertices following the arrows and so on. So, this is an example of a strongly connected graph, and if I take this as an example, you can see the arrows and you can clearly understand that starting from any vertex A, B, C and D, you can reach any other vertex. And following this definition, a graph which is not strongly connected, an example I have set over here. From A I can reach B, fine. From A I can also reach C, fine. Or I can reach from A to C here straight away. But if I decide from C I want to go to A, that is not possible if I follow the arrows. From C I cannot go this way, not permitted, I also cannot go this way. Therefore, this is an example of a graph which is not strongly connected. Now, I put a question, if I do a complementary of a strongly connected graph, will I get another graph which is also strongly connected? Let us take an example. This is an example of GSC, and if I take its complementary graph, I mean to say all the arrows will be reversed. I can easily see that this also strongly connected. Now, I take another example, a graph which is not strongly connected, and if I do complementary, will I get a strongly connected graph or not strongly connected graph? For example, this is a graph which is not strongly connected. Now, I am going to do its complementary operation. I write here G not strongly connected is made its complementary not strongly connected. So, what will happen here? All the arrows will change their directions. So, this will change to this will change to that, this will change to this. If I want to reach from A dash to B dash is not possible. Therefore, that a graph which is not strongly connected, its complementary will also be not strongly connected. We will now see the concept of subgraph. Take a graph over here with 6 vertices and so many edges, and I represent this H graph as a sum of the vertices and the edges. Now, a subgraph is another graph H dash with x dash are the vertices, f dash are the edges, such that x dash is a subset of x, f dash is a subset of f. That means, in simple language, out of so many vertices, I will pick up only few. For example, here I have picked up only 3, 5, 4 and 2, 3, 5, 4 and 2. Only few are picked up. If f is the vertices 1, 2, 3, 4, 5 and 6, then f dash is equal to 3, 2, 5 and 4. And what about the edges? we have the edges 35, 32, 12, 24, 45 and 56, and f dash is 32, 24, 45 and 53. 35 is same as 53. Okay. So, we can see here x dash is a subset of x and f dash is a subset of f. Now, if I just pick up this line 34 here and with two vertices 3, 4, this is also another subgraph of the graph H double dash, another subgraph. We will now see the concept of the reachability matrix. Consider a graph like this, which is a digraph and the arrows are showing the movement direction from vertex A to B, something can move, from C to B, things can move, from D to C, things can move, and so on. Now, we will create a square matrix with all the vertices. So, ABCD is stated here, ABCD is stated here. Now, the question is, from A can I reach to A? Let us say yes, and yes means 1, 0 will mean no. From A I am reaching to A, a loop is required, but in this case let us say loop is not required. Standing in A means I have reached A. Now, from A to B can I reach? Yes, I can see an arrow, therefore 1 is added here. Can I reach from A to C? The answer is yes, first A to D, then D to C. So, here I put 1. Can I reach A to D? Yes, of course I can reach, there is an arrow here. So, it is 1. Can I reach from A to E? Yes, we can reach A to E. So, it is 1. So, what is the basic difference between the matrix that I showed in the very beginning for such graph and this matrix is that also needs to be understood. In the previous case, we have written let us say A, B, C, D, E, and here A, B, C, D, E. So, we wrote that from A to E there is no direct connection, so I put here 0. But you can see in this case from A to E I am putting 1. So, that is the difference. From A to D I will write plus 1, and from D to A I will write minus 1. You can see here D to A is minus 1, whereas here for D to A is 0. So, you can see a difference between this matrix and the reachability matrix. Both have their own values. So, if I put a question here, is this matrix symmetric or antisymmetric or none of them? Can a reachability matrix be symmetric? We have been talking about the inversion of the rock succession. Suppose that happens, what happens to the coexistence graph? A and B are the two taxa joined by an edge and we are calling it as the coexistence graph. Now, if the entire lithology is tilted, the graph remains the same, no change takes place, because those taxa in the same horizon, if the entire tilting of the lithology is considered, then they still remain in the same horizon. Now, we will take a biostratigraphic graph. There are three taxa A, B and C. A is either below C or A and C in the same level, and A and B are in the same level. Then what it means, C, A and B, this is one possibility. The other possibility is that A and B in the same level because they are joined by a line, C is above A. So, this is one possibility. The second is A and C in the same level, A, B by joining a line, that means A, B, C all in the same level. Now, here if we change the arrow direction, what is the difference between this biostratigraphic graph G over here and here G T, let us say some operation is done and the arrow direction is reversed? What it will mean that C lies below, A can lie above, A and B occur together. This is one possible succession. The other is that C and A lie in the same level and so also B. This is the another succession. In fact, there is a single horizon is shown. So, out of these two, what I find common is this possibility, and between the other two sets of possibilities here, what it means that they are related by the operation of inversion. If that is being done, then I will remove old and young, and I can write bottom and top, and here I can write bottom and top, and here also for the sake of similar presentation bottom and top, and here also bottom and top. Suppose we want to decide to remove vertices from a coexistence graph. Now, we have to understand why should we remove. Suppose we worked on fossils P, Q and R, later we decide based on our studies that this R is to be avoided. Suppose some geologist says R is a reworked fossil, it has come from outside and in fact it is broken, so R has to be avoided. In that case, how to operate has to be checked. Here we are dealing with a graph, coexistence graph with 4 taxa A, B, C, D. Now we decide to remove D. So you can see after removal what has happened, not only D will go out, but naturally the edges that were connecting D, these three AD, BD and DC has also to be vanished. AD, BD and DC to be vanished. I will start with the coexistence graph that earlier we were dealing 1, 2, 3, 4, 5, 6, 7, 8, and here suppose we decide we want to delete vertex 3. The operation will be simple. Which things will get deleted? I am marking in red. This vertex will be deleted, this edge will go away, this edge will go away and this edge will go away. We get this graph which can be called as a subgraph. That means when we are removing some taxa from an existing graph, we are moving towards a subgraph. Now let us take another example. We are dealing with the same graph with 8 taxa. Now we decide we want to delete vertex 5. So what are the things to go away? I am marking in red this vertex 5, this line and that line. Graph is going to be separated into 2 disjoint graphs. Here 6, 7, 8 will be staying. So what will stay? I am marking, and this will stay. What is the simple geological meaning? Can you give an example? And it looks like we are having now 2 separate data sets. If we look at the matrix of this graph, we were deleting, and those are marked by the red rectangles. If I draw these rectangles, we find that we are separating the entire matrix into 4 parts, part 1, part 2, part 3 and part 4. And interestingly, in these 2 parts, you see this is basically a null submatrix, this is a null submatrix, and the other parts are not null submatrices. This is the one and that is the other. I am dealing with 1, 2, 3 and 4 and their matrix, this red box only. And what about 6, 7 and 8? 6, 7, 8 here, 6, 7, 8 here. I have got this matrix representing the 6, 7, 8 and their connections. So this is a special case where we got the null submatrices at the 2 corners here and over there, and since that was found and in between 5 as a column and 5 as a row were there, therefore we got the 2 disjoint graphs as a part of a bigger graph. That is what I write. Since I am observing 2 null submatrices at the 2 sides, therefore removing 5 we will get 2 disjoint graph. In the previous case, when we removed vertex 3, we did not get 2 disjoint graphs, and it can be reflected within the starting matrix. Here is 3, if I draw a column here and here is 3, I do not get at the 2 sides null submatrices. So in this side, this is not a null matrix because I can see 1 and 1, and on the other side also, say this side, this is not a null matrix because I get 1. So this gives an indication that if vertex 3 is removed, we will not get 2 disjoint sets of vertices. Now, suppose 2 and 6 were connected. See, 2 and 6 have been connected, is a new connection. Look at the graph earlier, 2 and 6 were not connected. Suppose in our study we find that they occur in the same level, then 2 and 6 can be connected. Write down the adjacency matrix. It is an easy job and it is your exercise. So, you can do that looking at this graph only, and then after that you remove node 5 or the vertex 5. Suppose this is the situation and now you are removing node 5. This time disjoint matrices do not come out, and you can look at the matrix of this graph. You will not find two sub matrices with all the element zeros across the vertex 5, and it should be checked by you. So, in this way, looking at the matrix you can have idea, need not draw the graph. We are dealing with only 8 species. Suppose we are dealing with large data with hundreds of nodes, then from the matrix there is no need to construct the graph. Simply looking at the matrix, and with this knowledge you can work out. Note that if we remove the terminal vertices, example 1 or 8, here is 8 and here is 1, from the graph we can clearly see that we are not creating two disjoint sets of vertices or two disjoint graphs. Just brushing up what has been done earlier in different ways possible, so that things become clear. Say from P1 section we get a succession A at the bottom, B at the top, and in P2 succession we get B at the bottom, C at the top. Then from P1 section, suppose we are drawing section wise graph, then A, B, this can be done, A lies below B, B towards C is given. Now consider them together. Suppose I am compiling information from here and here, and in this situation it is like this. This is T1 time, this is T2 time, this is T3 time, and this is T4 time, and the observation is T1 is older than T2, and then we find T3 and T4. So, this will give us a confidence to develop a succession like this A, B, C. So, then how it will be represented? This will be the representation, as if this graph G1 and this graph G2 are joined with a common vertex B without any problem. And indeed in some section we find that such is the case. Below C lies B, below B lies A, that means below C lies A, then we will get a confidence to join this line and make this arrow. Now, if I put a question calling it as G4, calling it as G3, are Gi, that means G1, G2, G3, G4 strongly connected? The answer is no, because from A to B I can reach, from here I cannot reach B to A, B to C I can reach, but C to B is not possible. In G3 case I can reach from A to B, B to C, but from B to A movement is not possible. And here after we have combined, from C to A movement is not possible. So, what we have seen in these cases, we are not dealing with the strongly connected graph. Let us consider another situation. Suppose we have got various sections P1, P2, P3 and P4, these are the vertical sections, and we are seeing the species delta and rectangle, two kinds of species given by symbols. And if I join these as lines, this red line actually you can see crosses this blue line, and this looks strange because here this triangle one is younger, this one is older, and if you are observing here the triangle one is older and this one is younger. What can be the reason? What can be the explanation? Here we go for the lowest appearance amongst all the known sections of triangle. This is the lowest appearance and we call it the true chronological appearance. And same thing we do with the rectangle. Where is the lowest appearance? By the way, here this rectangle does not appear possible. Here is the lowest appearance. So, I draw this and call it as the true chronological appearance. So, if I draw the diagrams here, this is for the rectangle and this is for the triangle. So, what can be the interpretation? From this place onward, the rectangle is persisting, and from this place onward up to this much, and the triangle is persisting up to this much. In this connection, let us see the Lazarus effect. Consider a vertical section of rock. Say this is a vertical section and we are dealing with a transitional marine non-marine environment, coastal region, and in such places the contact between the non-marine rock and the marine rock in vertical section appears in a zigzag pattern. Suppose in this transitional environment we have drilled a well, then what do we observe is that marine rock, non-marine rock, marine rock, non-marine rock and marine rock, such alteration can be observed. Now imagine there is a certain kind of species that can stay only in a marine environment. When the rock is marine, it got deposited. When it is non-marine, the species was not there, and again when there was a marine deposition, the species reappears. So, this reappearance, now if you are observing only this much of succession, do not think that the species disappeared over here. It did not disappear, it continued actually, but it was not recorded, it was there in the on the earth. So, such omission of the fossil in transitional marine non-marine environment is called the Lazarus effect. So, absence of fossil does not mean that the organism got extinct.